Hmm. Chapter 10. I wonder what that's about.
Out on the streets, that's where we meet. You make the night, I always love the light. Time for bills, abuse the sales. Get in our way, we'll put you on your shell. Another day, some other way. We're gonna go, but then see you again. I've had enough, we've had enough. Call me, she said. I knew right from the beginning that you would not win. I knew right from the start you wouldn't go through my heart. Round and round, with love upon the way down, getting tired. Round and round, what goes around goes around. I'll tell you why.
Well, I don't know if you figured it out by now, but apparently chapter 10 is about circles. You may be thinking to yourself, I know about circles, they're round. You would be right. But there are a lot of things about circles you probably don't know. And in fact, I think about almost 20 theorems worth of things about circles. And so we've got quite a bit to talk about this chapter. This first part of the chapter is really just going to talk about a little bit of vocabulary and then a couple of theorems based on tangent lines. What are tangent? So we'll talk about that today. And then, like I said, a lot of vocab, and that'll be about it. So here is our official definition for a circle: the set of all points in a plane that are equidistant from a given point, called the center of the circle. So if I take a bunch of points on a flat surface, on a plane, and put them so that they're all the exact same distance away from a central point, we will get a collection of points called a circle. This definition should seem somewhat familiar because last chapter we found the surface area and the volume of something called a sphere, which was the set of all points in space that were equidistant from a given point. So what that did is basically make a three-dimensional object that we call a sphere. And almost the same definition, just the difference between 2 dimensions and 3 dimensions, really. The notation for a circle is just a little O with a dot in the middle to show that it's not, excuse me, actually O. It actually is a circle. And then the letter, which is the center of the circle. So once again, it has to be capital because we name points with capitals, but this would be circle A because the center is point A. Circles are actually studied at a higher level if you get into math analysis, where you'll start talking about conic sections, sections of a cone. We just found surface area and volumes of cone last chapter. If you start making cross sections of cones at different angles, you'll get different conic sections. You get circles, ellipses, parabolas, and hyperbolas. Circles are actually special cases of ellipses. They just happen to be when you're cutting through the lateral surface of the cone exactly parallel to the base. Ellipses are where you have a little bit of slant to it, and so that's what gives them that elliptical shape. You may be thinking to yourself, parabolas? I know parabolas. We studied those in Algebra 1, and you did. You probably studied the standard form, ax squared plus bx plus c. The vertex form, probably, ax minus h squared plus k. But as you can see, at the bottom here, there's a conic form. And depending on whether you have an x squared or a y squared, these things can go up and down, or they can go left and right. So there's even more advanced forms of parabolas as well, but that is not our concern of today. Here's another picture of the conic sections where you can see the cone being sliced to create these different guys. And there's that circle we're going to be talking about today and for the rest of the chapter. So the radius of a circle is something you're familiar with. We had to use it a whole lot to find things like area and volume of different figures, but it's actually a multidimensional definition. So let's break it down. You can see the part in yellow here, a segment whose endpoints are the center of the circle and the point on a circle. So we're defining it as an object, a physical object, a line segment, specifically with endpoints at the center and then anywhere on the circle. But if you notice the second part of this definition, the distance from the center to any point on the circle, now we're talking about a distance, which is a quantitative description of an object. So we could call it a line segment, or we could call it a distance. It's kind of two different things, but they're related because it's the distance of the radius, right? So it's like the definition of itself in a way. The plural of radius is radii, and apparently in Spanish, radius is radio. So how about that? Here's a little question for you: is segment PQ the radius, or is distance PQ the radius? And of course, the answer is yes. If you use the first part of the definition regarding line segments, line segment PQ is a radius. But if you use the second part of the definition regarding distances, the length of PQ is the radius. Notice the slight difference in notation. Something we studied all the way back in chapter 1 last semester when we were still at school. Good times, right? You've actually seen the definition of a chord all the way back in chapter 11 when we were doing area, because you have to find the area of something called a segment of a circle. And a segment of a circle was defined as the area between a chord of a circle and the arc that chord intersects. So in this case, it would be arc ST, right? Well, now we're just defining that chord officially. A segment who has two endpoints on the circle. Segment whose endpoints are on the circle. Okay, ST is a chord in a circle. QR is a chord. Obviously, you could pick any 2 points on the circle, so there would be infinitely many different chords. QR is a special chord on the circle, probably the most famous of all chords because it goes through the center. And so the diameter is a special chord that passes through the center of a circle. It has to be the longest possible chord you can get because it goes across at the furthest distance through the circle. Very good question for you. How many circle line relationships exist on a plane? Why don't you pause this and think about that for a couple minutes, and then unpause it, and I'll tell you if you were right or not. Were you right? I don't know. If you said the answer was 3, then you were right. Congratulations, because one relationship is what you see right now, where the line does not intersect the circle at all. That's actually one relationship. Another relationship is where that line enters the circle, which means it has to exit the circle, and they actually share 2 intersection points, right? 1, 2. Now, the third relationship is actually probably the most special, And that's where you get a line that just bounces off a single point. So it never really enters the circle. It just grazes it at a single point. This is what we call a tangent line. We're going to define that in just a second, which of course is what section 10.1 today is all about, tangent properties. So those are your three possible relationships. And the two that you see here, tangent, and then this one that crosses twice, secant, are two definitions coming up. This one doesn't really have a name. So here's your definition of a secant line. A line that intersects a circle at 2 points. And you can see that's exactly what we have here. Line M is intersecting the circle at 2 distinct points, 1, 2, and we call that a secant line. I've also seen the definition described as a line that contains a chord, because if it contains a chord, right, here's the chord, it would have to have intersected the circle twice. Here's the definition of the tangent line, a line in a plane that intersects a circle at exactly 1 point. And we call that point the point of tangency. So that point right there where it intersects is the point of tangency. And we could have that line going, you know, at any of the infinitely many points along the circle. Here's a tangent line that hits just 1 point, maybe right here. Now it does have to be on the same plane. If you imagine a line coming from behind your screen straight at your face, it could hit the circle at a point on the edge, right? But it would not be on the same plane as the circle, and so that would not be considered a tangent line, just a line that it was not coplanar with the circle. Tangents and secants are things that you will see in the future as you get close to calculus and then into calculus, because we leave the idea of a circle, but we keep those two lines with us. What we're doing is we're looking at how functions change, how the rate of change of functions will slow down and decrease and increase over time. And you can see that with this picture right here, we've got 2 points. And if I look at the change between these 2 points on the line, I'm basically looking at the slope of a secant line. But if I'm looking at the rate of change not between 2 points, but at an exact single point, we call this instantaneous change, then we're looking at the slope of a tangent line. So this is a huge conversation in math analysis, and then into calculus, this is really part of the foundation of what calculus is all about. So something to look forward to. As you can see in this second image, along the same curve, you see many different tangent lines, different tangent slopes along the way, but we're not worried about tangents on a curve. We're only worried about tangents on a circle. And here you see a circle that has a whole bunch of things going on. Let's identify, let's see if our terminology is looking good, okay? What is AC? Segment AC, right? Segment AC. Well, it's a segment. One endpoint is the center, one endpoint is on the circle. And so if you said, well, she answered that by definition, that would have to be a radius, you win the game. What about segment AB? So this time, we're actually going all the way across. Well, this time the endpoints are points on the circle. So if you said, oh, well, that would be chord by definition, you would be primarily correct. However, because this particular chord goes through the center of the circle, we can be a little more specific. Say that chord is special. It is a diameter. What about ray DE, right? Ray DE. Know your notation. We haven't seen rays in a while. Well, let's take a look. And it looks like we're starting up here at D. and then we're going down through E. And look at this. We hit point B. We hit 1 point exactly on the circle. Look at that. That's a special situation, isn't it? That has to be a tangent. Now, we wouldn't call it a tangent line in this case because it is a ray, but we could certainly call it a tangent ray. So that would be a tangent ray. And then finally, what about AE? So AE is a line. Okay, look at the notation. Line AE from A through E. Well, that's a line that actually goes through circle C 2 times, twice. And so I think we would call that a secant line. And hopefully the vocabulary is coming to you. Well, I'd like to remind you at this point, you have all of this vocabulary in your blue vocabulary packet. You may even have some really pretty pictures along the way, and take advantage of that information that's there for you. Flip through and study it so you get these new terms down, because there are more new terms in this chapter than probably a normal chapter. Here's a quick question we can just kind of buzz through really quickly. Just talking about radii of circles, and you can see that we're just going by 1 unit. So the radius of circle A would appear to be 1, 2, 3. The diameter of A then would probably be twice that, right? 6. Radius of B would be 2, and the diameter of B would be 4. Now, one thing that I would throw at you is that look over here, circle D has a radius of 2, just like circle B. All that 2 circles need to be congruent is a equal radius, a congruent radius. If they have the same radius, they're congruent circles. And that's one thing to keep in mind. Congruent circles or radius circles that have the same radius. So I think that's good for that. Here's another question for you. How many circle-circle relationships exist? So we talked about circle-line relationships. There were 3 of them. How many circle-circle relationships do you think there exist? So why don't you go ahead and pause this for a second and think through that, and then unpause it, and I'll tell you if you were right or not. All right, did you say there are 4? If you said that there are 4, you would have been wrong, because once again, there are 3. There are 3 again. And one of them is where the circles don't have anything in common. They're on the same plane, but they do not intersect. Okay. The second example is where they actually intersect twice, right? They have 2 points of intersection, 1, 2. And that could happen many different ways. But then, of course, the special one is where they share just that 1 point. And we would call those tangent circles, And that leads us into this little picture. If the circles do have 2 points of intersection, we say, cool, those circles intersect twice. And you kind of start to get something like a Venn diagram that I know you've seen before. If they do intersect exactly 1, just like we call that line a tangent line, we would call these tangent circles. Now, notice there's a difference. We could have a circle that's inside of another circle that's tangent, or a circle that's outside of the other circle. We would call these interior tangent circles, and we would call these exterior tangent circles. And then, of course, we would have circles that have no points of intersection, which isn't really all that interesting unless one circle is entirely in the other circle and they have the same center. We then call them concentric circles. And, I think we've referenced that before. That's if you take the area between concentric circles, we call that an annulus. And you guys have found the area of those before. So some more terminology for you. Here's some common tangent lines. Okay, so if a line is simultaneously tangent to multiple circles, we'll call it a common tangent line. If it weaves between the circles, like this one on the left, We'll call that an interior common tangent because it's between inside the circles. And if it doesn't, we'll call it an exterior common tangent. Once again, I believe all of these are in the vocabulary packet. So continue to go over those over the next couple weeks to get this terminology down. Here's a fun little activity for you. You should go ahead and pause this and see if you can answer this. How many different common tangents are possible in each of these scenarios? Go ahead and think that through, give a pause, and then come back, and we'll see how you did. Hey, are you back? The funny thing is I never paused anything. You paused. But anyway, on this first one, I think most people get 2 right away. They're like, oh, yeah. There's one that could be up here on the top. And then there's one that could be down here, kind of below. So I see 2 tangents. But if you really think through it, there's room between these 2 circles. Well, probably don't want that one. Let's choose this one. So I could have one that kind of comes down through here, that's tangent to both circles, but I could also have one that kind of cuts through like that, that's tangent to both circles. So there's actually 4. If you got 4 for A, then you rocked it, you win. Congratulations. For B, you actually end up with almost the same deal because you have one above and one below. But then when you go between them, there's only a point. These are actually tangent circles, right? Exterior tangent circles. And so there is room, but only room for one line to go through there. And so if you said there were 3 on this one, you win, okay? And then when you move to figure C, well, now we can still have the upper common tangent, exterior common tangent line, and the one on the bottom. But there's no room in between now. These circles intersect twice, and so we don't have any room for more than just 2. 2 scenarios that they did not include are what if the circles are interior to each other? Well, if you have interior tangent circles, you could have a line that's tangent to the circles at that point of tangency. So you could have one. If the circles are just, one of them's just flat inside the other one, they don't share any points, there's no way to have a tangent to both. Because to be tangent to the inner circle, you'd have to enter inside of the bigger circle, which means that it would become a secant line for the bigger circle, right? So anyway, a little bonus fun there on a Tuesday morning. Moving on, let's do our theorems. Okay, the first theorem tells us that if we have a line that's tangent to a circle, then it must be what? Well, the picture gives it away, doesn't it? What is the relationship to this radius drawn to that tangent line? We see a little box right there. We know that that means a right angle. And so the line would have to be perpendicular to the radius of the circle that goes to that point of tangency. Now notice this is an if and only if. We haven't seen these types of theorems really since first semester when we were doing a lot more theorems that weren't just formulas, right? You'll see a lot more theorems in this chapter that will remind you of first semester than most of the theorems that you've seen that are more like area and volume formulas. The if and only if means it works in both directions. So just to remind you that that biconditional statement means that if the line is tangent to the circle, then when I draw the radius to that point, it has to be perpendicular. But it also means that if I have a radius that hits a line at a point and it creates a perpendicular relationship, that line has to be a tangent. It can't be a secant. It has to be a tangent. So it works in both directions, okay? Here are a couple examples where we could use this. Is this segment ST? Is this segment ST here? Is that segment tangent to circle P? Well, only if, right? Only if this is a right angle right here. Well, hey, when I drew segment SP, I actually ended up making a triangle. So if the two shorter, we call them legs, if it was a right triangle, if the two shorter legs squared and added together equals the longer side squared, then by the triangle or the Pythagorean theorem converse, it has to be a right triangle, right? And that would mean T would have to be a right angle. And so that's really what you do. You just have to use the Pythagorean theorem to test it out. Now at this point, I think they're thinking, oh, yeah, it's a primitive, so obviously that's true. Now we don't really know that's true because that's one of the bigger primitives that most of you guys probably don't have memorized. But if we tested it out, guess what? It's a good deal. So yes, segment ST is a tangent because it is perpendicular to the radius drawn to that point of tangency. Here's another example, same premise, okay? But this time, they tell us AB is tangent, and they want us to solve for the radius of the circle, okay? Now notice that this radius is part of, it's one leg of this right triangle. I mean, we know that this is a right angle right here by the theorem, okay? But one of the radii is a leg. The other radii is part of the hypotenuse. So we should be able to set up an equation once again with the Pythagorean theorem here, which uses that radius. You know, as a triangle, I know that, you know, side AB squared plus side BC squared equals side AC squared, right? But I know that AB is 80, and I know that BC is R. So R squared plus 80 squared equals what? Well, this entire side here, okay, would be 50 plus R, or R plus 50. I see a lot of people, not a lot, but enough, who will tell me it's 50, will tell me it's 50 R, right? 50 times R. And that doesn't make any sense. 50 times R would be this little green segment multiplied 50 times by itself. That's not what this is. It's 50 plus R, or R plus 50. Cool. So let's plug that in. So this is all good until people try to square R plus 50. Okay. And then we have to remember that if you square a binomial, you don't just square the two parts. So, as the young lady says, stop trying to make it happen, okay? That's not how algebra works, unfortunately. If we go down here, we notice that what we're squaring is not the 50 or the R, but the parentheses. We have to multiply the entire binomial times itself. That means we need the FOIL. And then you can combine the 50 R's to make 100 R. So this is what we would end up with. R squared plus 100 R plus 2500. A lot of people just square the 50 and the R, and this is what they get. And then those R's cancel out, which happens on the next line, and you have 2500 equals 6400, which is never true, and you get confused. And sometimes I find little teardrops on the quizzes, and it's a sad thing. So do your algebra correctly, okay? Don't try to make that happen. Ain't gonna happen, ever, all right? But now that I do have the 100R in there, when the R squareds do cancel, I just get 100R equals 3,900, which of course means that R is just 39. Is that always going to be an integer answer? No, of course not, but in this case, thank you. We'll take it. All right, last theorem of the day, theorem 10.2. A little more straightforward than the last one. Tangent segments from a common external point are what? So here I have point S external. I've got a tangent to a point R and a point T. What do you think about those two pieces? And if you think that they're the same length, if you think they're congruent, you are absolutely correct. So if I take any point outside of a circle, and I draw a tangent to one edge of the circle and then the other edge of the circle, okay, those would have to be the same length, according to this definition. I can prove it for you. Um, and I know most of you are like, no, you really don't need to do that, but it's what I do. So here's our picture here. How can I prove that ST and SR are indeed congruent? Well, first of all, since we have theorem 10.1, let's use it, okay? It tells me that if I draw a radius to a point of tangency, that it would have to create a perpendicular relationship, right, to the tangent line, or in this case, the tangent segments, which is cool. I just made a shape that has two right angles, which isn't that cool until I add one more segment in there. Now I have two right triangles. Huh, very cool. These two segments are radii. We know that every radius in a circle is congruent to every other radius. And I also know by one of your favorite properties from semester 1, the reflexive property of congruence, that PS is congruent to itself. Now, normally that would not be enough information, right? One side and another side. If I use the angle, it's ASS, but we know that's bad. But remember, we had a special relationship for right triangles called HL, the HL theorem, the hypotenuse leg theorem. And so I've now proven that these two triangles, PRS and PTS, are congruent by the HL theorem, which means that by CPCTC, corresponding parts of congruent triangles are congruent, that RS has to be congruent to TS. And that's the proof. I'm sure that brightened your day. I'm glad I could add sunshine. So here's an example where we use this. It tells us that RS and RT are tangent segments. That means they have to be congruent. So I guess we could set them equal to each other. Ooh, that's a tough equation. Subtract 4, divide by 3, and you're done. So you might see a couple like that. And that's it. I hope that you understood this stuff. Obviously, if there's any questions, please meet me at about 2 o'clock, and I'll do a geometry help session, and the information, links, and all that kind of stuff will certainly be posted on the classroom. Welcome back from break. I hope it was a decent break, and we will see you around.
She said, I knew right from the beginning that you would not win. I knew right from the start you put an arrow through my heart. Around and around.